Today we're going to be talking about the precise definition of the limit for multivariable functions. And in this particular problem, we've been asked to show that the limit either does not exist, dne, or if we think it does exist, to use the epsilon-delta definition, which is also the precise definition, to prove that the limit exists. And as a reminder, I've written the formula here for the precise definition of the limit for multivariable functions. But before we go into multivariable functions with this epsilon-delta definition, I want to make sure that we review quickly the precise definition of the limit for single variable functions, because I think it'll help us to transition directly from that single variable definition into this multivariable definition. So down below here, I've written the precise definition of the limit for single variable functions. And as a reminder, it tells us that if we're taking the limit of a function f of x, as x approaches some random point a here, then the limit is going to be equal to L. Now we're not going to go through a whole problem with this, but as a reminder, looking at this graph I've drawn on the left here on the bottom is the graph that represents the precise definition of the limit for single variable functions. And what it tells us is that we have this point A here and the limit L. And so it says that if we take any value of x, right, and x is getting closer and closer to A. So if we say that our point x is here, and then the point x is here, and then the point x is here, in other words, x is approaching A, x is getting closer and closer to A, then what we expect is that the value of the function I've drawn here in orange, but the value of the function will get closer and closer to L. What we're looking to do here is kind of to define the interval around A and around L, because if we have this defined interval, we don't worry about anything outside of the interval. We're just looking in between these blue dotted lines here and in between these teal dotted lines here. If we kind of define this interval and we always stay inside it, and we can prove that everywhere inside this interval as x gets closer to A, f of x gets closer to L, then we can use the precise definition of the limit to prove that the limit exists, to prove that the limit as x approaches A is actually equal to L. And therefore, what the precise definition of the limit tells you is that if you pick any x inside these blue dotted lines here, inside the values a minus delta and a plus delta, right here, a plus delta, if you pick any x value inside these two values, so let's say we pick an x value right here and we call this x, that's going to be our value. If we pick a value for x inside this interval, then when we plug that into our function, it's going to return a value inside this epsilon range. So in other words, between L minus epsilon and L plus epsilon, it's going to give us a value back that's between these two values. So maybe somewhere like right here. And if we were to pick a value even closer, so let's say if we were to pick a value even closer to A right here, we should get a value back that's even closer to L, so right here. Now the only important thing to remember here is that the precise definition of the limit has dictated this epsilon range, right? These distances here, this distance here, and this distance here are the same. They're both equal to epsilon, and so we get L minus epsilon and L plus epsilon. So we've defined this epsilon range, and we know we have to stay within that. The problem is that this statement here, A minus delta and A plus delta, this is not really true, because notice how these distances, this one here and this one here, are different. These distances are unequal. And if we say that this value is delta, this distance right here, and we move left of A, that same distance delta, if we approximate it so it looks like it's about maybe that long or so, now immediately we're outside of this blue dotted line. We're all the way over here. And if we go up that far and then over to the left, notice we are outside of that epsilon range. We're outside of L minus epsilon, and that is not okay. We can't do that. So what we have to do is recognize that this distance here, this one, is sort of the limiting factor of delta. We need to take the smaller distance of delta, because if we move that same distance to the right of A, right, we take that same distance and it looks like it's about this long here, we approximate that distance moving to the right, we're still inside this blue dotted line, which means we're still going to be inside our epsilon range. So we want this value right here, this distance right here, to be the value for delta we pick. And if we can solve for that value of delta, and we know that we always stay within a delta distance away from A, then we guarantee ourselves that we're always going to be within an epsilon distance away from L. And we know that as we decrease the delta distance, as we move in closer and closer to A, which we looked at right here, then we're going to move in closer and closer to L. So that's the precise definition of the limit for a single variable function. But what about for a multivariable function? Well, we're just going to take everything that we learned here and transpose it onto a three-dimensional coordinate system. So instead of just our x and y axes, we now have our x, y, and z axes in a three-dimensional coordinate system. But let's say we have some function, this orange line is our function here, and it's in a three-dimensional coordinate system. Instead of just that single point A, we now have a three-dimensional coordinate point A, B. So A becomes this coordinate point here, A, B, in three-dimensional space. We want to say as the coordinate point x, y approaches some other coordinate point A, B, in this case it's 0, 0, but as we approach A, B, we want the limit of the function to equal L. So we go up and over and along the z-axis here, that's going to give us the value of the limit at L. So as xy approaches AB, the limit is L. Now we're going to do the same thing. We're going to move out along the z-axis a distance of epsilon away from L, right? This distance of epsilon here. So this value is going to be L plus epsilon, and this value is going to be L minus epsilon. And what we're doing is we're saying that if we want to stay inside this range, if we want the values of the limit to be between L minus epsilon and L plus epsilon, then we have to stay inside this circle. So before we said that we had to stay inside these two blue dotted lines here, these two. But now that we have three-dimensional coordinate space, instead of those two blue lines, we need to stay inside of this blue circle. This blue circle has the radius of delta. This radius of the circle right here is delta. So instead of just the distance between A and one of these blue lines being delta, it's the distance between the point AB and the edge of this blue circle that's delta. So that radius is delta. And the precise definition of the limit for multivariable functions tells us that I can find a value for delta such that as long as I pick a value inside this circle, I'm going to get back a value that's inside this epsilon range, that's in this range right here. So again, if I pick an x value right here, somewhere inside the circle, and I go up and over here, my limit maybe is going to be right about here. If I pick a value even closer to the point AB that's inside the circle, then my limit is going to be even closer to the point L. And so what this tells me is that as I decrease delta, as this circle gets smaller and smaller and smaller, as I shrink that radius, as I shrink delta, and I bring this circle in closer to this point AB and that circle gets smaller, then my epsilon range is going to get smaller until finally I realize that when I'm right on top of this point, AB, my limit is going to be L. So that's the general concept of the precise definition of the limit for multivariable functions. Let's talk about how to get from this formula, the formula for the precise definition of the limit for single variable functions, to the same thing for multivariable functions. And now that we understand this, it's going to be pretty easy. So first of all, let's look at this part right here. We say, then the absolute value of f of x minus L is going to be less than epsilon. Well, notice that everything is exactly the same as it is up in this multivariable definition, except that we have, instead of a function in one variable, f of x, we have a function in two variables, f of xy. And that makes sense because we've just added a variable. We've gone from single variable to multivariable, and so we just swap out f of x for f of xy, and instead of plugging this function into our precise definition here, we're going to plug in this function right here to our precise definition. So that's easy. Let's look at the first part now. If 0 less than the absolute value of x minus a less than delta. Well, if we compare that to the multivariable version, we see that 0 and delta are the same, our inequality is the same, except for the value in the middle. Here we have just the absolute value of x minus a, and here we have this big square root value here. Well, the reason we have this value x minus a here, absolute value of x minus a, is because remember, we took this point here, x, right, that was inside our delta interval, and we had this value here of a, so this purple and green dot here. So x minus a, if we take this value of x and we subtract a, we're going to get this positive value here, the distance between the two, this distance right here. So x minus a gives us the length of the segment between these two pieces, right? So x minus a gives us that positive distance. as long as that's positive and less than delta, and we know that delta is the distance all the way to the edge of our blue dotted interval here. So as long as that distance is shorter than the distance to the edge, then we know we're in our delta interval, which means we're going to be inside of our epsilon interval. And the reason we have these absolute value bars is because if we picked a value for x that was to the left of a, over here inside our delta range, and we said x minus a, this value of x right here is going to be less than this value of a, so we're going to get a negative value when we say x minus a, and so we take the absolute value to make that distance positive. That way we always have a positive distance, and that distance is always going to be greater than 0 but less than delta. Well, how do we transition that to our multivariable precise definition of the limit? Well, really, instead of this distance between x and a, we're looking for the distance between x and ab. In other words, the radius. This distance right here between our purple dot and our green dot is the radius of our circle. And we need that radius to be positive, greater than 0, but also less than delta. Well, remember that the equation of a circle, because this delta interval here is a circle, the equation of a circle is x minus a squared plus y minus b squared is equal to r squared, where r is the radius, and AB is the center of the circle. Well, we know AB is the center of the circle, right? That's the coordinate point that we're approaching. So AB is the center of the circle, r is the radius of the circle. Well, we want to solve for radius, right? Because we're interested in this radius distance here being positive, but also being less than delta. So in order to solve for the radius, we just take the square root of both sides, and we get r over here on the right-hand side. This goes away, and on the left-hand side, we just get the square root. So when we take the square root of both sides, r squared becomes r, and we get this square root over here on the left. And you'll notice that this square root value matches the square root value here that we have in the precise definition of the limit for multivariable functions. The reason we don't need to put it in absolute value bars like we do here is because this square root value is always going to give us a positive answer anyway. Because even if we get a negative value for x minus a, we're going to square it and get a positive. Even if we get a negative value for y minus b, we're going to square it and get a positive. So we'll always have a positive plus a positive, which will give us a positive underneath the square root sign. And taking the square root of a positive number will always give us a positive number. So we're always going to get something positive here between 0 and delta. So we don't need those absolute value brackets. We just solved for the radius of our delta circle. So now that we understand the precise definition of the limit for multivariable functions and how that was adapted from the precise definition of the limit for single variable functions, let's talk about how we're going to go about testing this limit to see whether or not it exists, and if we think it exists, how to use this precise definition of the limit to prove that it does exist. Now, with multivariable limits like this, our strategy is going to be a three-part process. First, we want to see if we can just plug in the point that we're approaching, in this case, 0, 0. If our function is continuous at this point, then we should just be able to plug it in, and if we can plug it in, then the value that results is the limit of this function as xy approaches the point 0, 0. So if we plug this in, we get 0 over 0. That tells us that we have a discontinuity at the point 0, 0. So we can't just plug in this value to get the value of the limit. So our second step is to try to show that the limit does not exist. So if it's not continuous, now we're going to look for two paths with different limits that will prove that the limit doesn't exist. So remember when we were dealing with single variable functions, we said that in order for the general limit to exist, the left-hand limit had to exist, the right-hand limit had to exist, and the left and the right-hand limit had to be equal to one another. If those things were all true, then the general limit existed. So similarly here, we have to show that the limit is the same value as we approach the point 0, 0 along every path. So before with single variable functions, we just had to show that the limit was the same as we approached from the left and from the right. But when we put that into a multivariable context, we have to show not just that we're approaching the same value from the left and the right, but from every path. So the way that we're going to test this is by approaching the point 0, 0 along several different paths. If we can show that approaching 0, 0 along two different paths gives two different answers for the limit, then we know immediately that the limit does not exist. So we're going to try to show that it does not exist. If we get the same value for the limit every time, no matter which path we approach along in our kind of random testing, then we'll move over to the precise definition of the limit to see if we can prove that it exists. So in this case, we're approaching the coordinate point 0, 0, which means we want to test approaching that point along paths that intersect that point. So for example, we could approach along the line y equals 0, or in other words, along the x-axis. So we have this point here, 0, 0, right? This is the value that we're approaching. We can approach this point along the x-axis, along this path. That's just one path that approaches the point 0, 0. If we approach along the x-axis, then we know that y is always equal to 0, right? Everywhere along the x-axis, y is equal to 0, which means that we can evaluate this function at the coordinate point x, 0. So in other words, if we say f of x, y, is equal to our function here, xy divided by the square root of x squared plus y squared, what we want to do is evaluate this function f of xy at f of x comma 0. So we're plugging in 0 for y, and we want to see what our result is. Well, plugging in 0 for y, we're going to get x times 0, which is just going to give us 0 in the numerator. In our denominator, this is going to be 0 squared when we plug in for y. So we're just going to be left with x squared. We get square root of x squared is just x. So we have 0 over x, or just 0. So what this tells us is that the limit of this function here, the limit of the function f of xy, is equal to 0 when we approach the point 0, 0, when we approach the origin along the x-axis. Remember though, we're trying to find two different paths that'll give us a different value for the limit. So what if we approach our point 0, 0 along the y-axis? If we approach it on this path here, on this line, well, that's going to be f of 0 comma y, because everywhere along the y-axis, x is equal to 0. So what we're going to do there is plug in 0 for x and leave y. We're going to plug that into our function f of xy. So plugging 0 in for x, we'll get 0 times y, or just 0 in the numerator. And in the denominator, when we plug in 0 for x, we get 0 here. So we're just left with the square root of y squared, or y, and we see that we get 0. So here we have to keep going, because when we approach along the x-axis, the limit looks like it's equal to 0. When we approach along the y-axis, the limit looks like it's equal to 0. We haven't found two different values yet. If these two paths, along the x-axis and along the y-axis, don't produce a different value, then oftentimes we like to test along the non-vertical line y equals mx. Remember, the equation of a line in slope-intercept form is y equals mx plus b. But in this case, our intercept, the intercept of the y-axis, is 0. So this value for b is just 0, and we get y equals mx. This is a non-vertical line, right, where m is the slope. It's a non-vertical line that passes through the origin. So this is a third path that approaches the origin, and it doesn't matter what the value of m is, but we could be approaching along this line or along this line, like here. It's just some non-vertical line. So what we do in that case, we say y is equal to mx, which means instead of y, we're going to be plugging in mx. So we're going to take f of x comma mx, like this. We substitute mx for y. When we do that, in our numerator here, we'll get x times mx, or mx squared. In our denominator, we're going to get the square root of x squared plus, we get mx quantity squared. When we square that, we'll get m squared x squared, like this. We can factor out an x squared from underneath our square root sign, and instead of this here, we'll get square root of x squared times 1 plus m squared, like this. So that's our new denominator. We can take the square root of the x squared, and we just get x out in front. This goes away. And now we can cancel an x from the numerator and denominator. We're just left with mx divided by, this squared goes away, this x goes away here, divided by square root of 1 plus m squared, like this. Now when we plug in 0 for x, right, because we're approaching the point 0, 0, when we plug in 0 for x, we're going to get 0 in the numerator, obviously. In our denominator, we're going to get square root of 1 plus m squared, which of course is going to be equal to 0. So we still haven't found a different value for the limit. I've moved our conclusions over here to the left so we have a little bit more room. The only other two paths along which we usually test before we move to the precise definition of the limit are these parabola paths that pass through the origin. So, for example, this parabola here that comes out of the origin this way, because that's an easy function, that's y equals x squared. So if we have y equals x squared, if this is y equals x squared here, then we're going to plug x squared in for y, and we're going to say f of x comma x squared is going to be equal to, plugging in x squared for y, we get x times x squared, or just x cubed, and in our denominator we get square root of x squared plus x squared. When we plug it in for y and square it, we get x to the fourth, like this. Now underneath our square root sign, we can factor out an x squared, so we get square root of x squared times 1 plus x squared. When we pull out the x squared, we'll cancel it from underneath here because the square root of x squared is just x, so we pull it out in front, and we're just left with, when we cancel an x from the numerator and denominator, x squared divided by the square root of 1 plus x squared. And here now when we plug in 0 for x, because we're approaching the point 0, 0, we get 0 in the numerator, and in the denominator we get the square root of 1 plus 0, or just the square root of 1, or 1, and that's equal to 0. So we say that f of x comma x squared is equal to 0. And we would do the same thing. We approach along the parabola x equals y squared, and when we have x equals y squared, we plug y squared in for x. So in other words, we do y squared comma y. And there, of course, we would just plug y squared in for x, and in the numerator here we would get y cubed. In the denominator we would get square root of y to the fourth plus y squared. And if we simplify that and evaluate at y equals 0, what we see is that we get the same thing here, 0 over 1, which is equal to 0. So we can say that f of y squared y is equal to 0. These are usually the paths along which we test for the limit when we're approaching the point 0, 0. Because they're all equal to 0 and we didn't find any discrepancy, we have to move to the precise definition of the limit. This is now our third step, to see if we can prove that the limit exists. So just to recap here, our three-step process with the precise definition of the limit for multivariable functions, we tried to just plug in the point 0, 0 to our function, but we got 0 over 0, which tells us that there's a discontinuity at the point 0, 0, so we can't just plug in. If we hadn't gotten an indeterminate form, then whatever value we did get would be the value of the limit and we'd be done. But because we had a discontinuity, we had to move on to this process, where we tried approaching the point 0, 0 along multiple paths. We were hoping to find two different values, because if any one of these values had been different than the others, we would have shown two different limits as we approach along different paths, and that would tell us that the limit did not exist, in the same way that with single variable calculus, if the left-hand limit and the right-hand limit were unequal, then we knew that the general limit didn't exist. But, of course, we've gotten all the same values here, so as far as we can tell, it looks like the limit is equal to 0. But we can't just continue picking paths and evaluating the limit this way, because there are an infinite number of paths along which we can approach the point 0, 0, and we can't test every single one of them manually. So the only way to prove that the limit exists is to use the precise definition of the limit. So that's where we are now. We need to go to the precise definition of the limit to really prove that the limit is equal to 0. So when it comes to using the precise definition of the limit, the first thing we're going to do is plug in the values that we know. We have this theorem here, this formula. If 0 less than this value, less than delta, then this value is less than epsilon. Well, we know f of x, y, that's our function, and we know a and b. And we even know what we think is our guess for L, right? We think that the limit is equal to 0 because we've gotten 0 for all of these here. So let's go ahead and plug that in and see what we're left with. So we're going to have if 0 less than the square root, the point we're approaching, AB, is 0, 0, right? This here is A, B. So we're going to plug in 0 for A and 0 for B, and as you can see, that's just going to leave us with x squared plus y squared underneath our square root. So we'll say x squared plus y squared, and that's going to be less than delta. So if this, then Here we have the absolute value of f of xy, so absolute value of our function here, x, y, divided by the square root of x squared plus y squared, like this, minus L. Well, we think that L is 0, so we just have minus 0, so we don't even have to write that. Then this less than epsilon. Now our ultimate goal with this is to find a relationship between delta and epsilon, and between this value here, square root of x squared plus y squared, and this value, absolute value of xy over square root of x squared plus y squared. So the way that we're going to do that is kind of by combining these inequalities in a way, and this is where things start to get a little bit tricky, and it just takes a lot of practice to get comfortable starting to manipulate these equations. But I want to show you sort of how to simplify this one and find a relationship between this value and this value. So the first thing we want to do is try to get rid of these absolute value bars if we can. So we're going to look at this whole fraction here. First of all, we realize that the denominator, we have the square root of two squared values, right? X squared and y squared. Well, even if x is negative and y is negative, we're going to square both of them and get a positive value. And when we add those positive values together, we'll of course get a positive value. And then taking the square root of a positive value, we'll still get a positive value. So what that tells us is that our denominator is always going to be positive. So there's no need to wrap it in absolute value brackets because it'll always be positive. So we can remove those and put them just here in the numerator. And while we're at it, we're going to go ahead and flip around this statement. We're saying if this, then this. What I want to do is say this inequality is true whenever this first inequality is true. To me, it makes a little bit more sense. So here's what we're going to do. We're going to say the absolute value of x times the absolute value of y divided by the square root of x squared plus y squared is less than epsilon whenever 0 is less than the square root of x squared plus y squared less than delta. So this value is always going to be less than epsilon whenever this is true, whenever this value is less than delta but also a positive value. The cool thing here is that we know, just like we already talked about, that this square root of x squared plus y squared, this is always going to be a positive value. There's no x, y value combination that would make this negative, so we don't even have to include this greater than 0 value here. We can just take that out like this and say that this is going to be less than epsilon whenever this is less than delta. Now, one thing we know, if we look at this absolute value of x right here, we know that absolute value of x is always going to be less than or equal to the square root of x squared plus y squared. And the reason we know that is because here we have x on both sides, right? Take any value and imagine this. If we take x to be 2, let's say x equals 2, over here on the left-hand side, you're going to have absolute value of 2, or just 2. Over here on the right-hand side, you're going to have 2 squared, which is 4. No matter whether y is negative or positive, this is going to turn into a positive value when we square it. So we're going to get 4 plus a positive value, so some value greater than 4. And then we're going to take the square root of that. And because the value underneath the square root sign is always going to be greater than or equal to 4, taking the square root is going to give us a value greater than or equal to 2, which is the value we have on the left-hand side. As a result, we know that the absolute value of x divided by the square root of x squared plus y squared, like this, that this value is always going to be less than or equal to 1. And the reason we know that is because we know down here that the numerator is going to be less than or equal to the denominator. So if they're equal, right, for example, if we have 3 over 3, well, that's equal to 1. If the numerator is less than the denominator, then we have things like 2/3, we have 0.75 over 1, things like that. All of these fraction values here are going to be less than or equal to 1. So really you can see that all we've done is examine this part of our fraction right here. We looked at just this piece without this absolute value of y. We've determined that this piece I've just outlined is going to be less than or equal to 1 always. And we know that the absolute value of y is going to be greater than or equal to 0, because no matter what value we plug in for y, negative or positive, these absolute value bars are going to make it positive, so this absolute value of y will be greater than or equal to 0. So when we take this whole fraction together, we know that this entire fraction, let's write it here, this entire fraction, absolute value of x times absolute value of y, divided by square root of x squared plus y squared, that this whole thing will be less than or equal to absolute value of y. And the reason we know that again is because this piece we outlined here is going to be less than 1. So when we take a value less than 1, like for example 0.5, and we multiply it by absolute value of y, it's going to reduce the absolute value of y. So absolute value of y is always going to be greater than this. If you take a number, let's say 3, and you multiply it by a value less than 1, like you multiply it by 0.5, the result is 1.5. 3 got reduced by 1.5, it gets smaller. So because we know that this outlined value right here, this outlined green value, is less than 1, then we know that this whole value is going to be less than or equal to the absolute value of y. Now, of course, here's something we always know about the absolute value of a single variable like this. This absolute value of y is always going to be less than or equal to the square root of y squared. And that should make sense to us because no matter what value we pick for y, let's say we pick 3, if we take 3 and square it, we get 9. The square root gives us 3. That's always going to be greater than or equal to the absolute value of 3, which is just 3. In this case, they're equal, and they're always going to be equal. But adding this in lets us get to our final step, which tells us that this value, the square root of y squared, is less than or equal to the square root of x squared plus y squared. We know that's true, of course, because if y is 2, for example, and we square it, we get 4. The square root is 2. Well, if it's 2 over here, but we add any positive value to it, for example, if x is also 2, then we're going to get the square root of 4 plus 4, the square root of 8, and the square root of 8 is always going to be more than the square root of just 4. But now we have a relationship between this square root of x squared plus y squared and this value here, absolute value x, absolute value y, over square root of x squared plus y squared. And of course, what we've shown with this inequality is that this value here is always going to be less than or equal to this value here. Now, if we just take an arbitrary relationship between epsilon and delta, and we say that delta, the radius of our circle right here, is equal to epsilon, the distance between the limit and this point here, if these two distances are equal to each other, then we can swap out epsilon for delta and vice versa. And that information, coupled with this inequality here, proves that the limit exists. And here's how. Because we can swap out epsilon and delta, because we say they're equal, right? Epsilon is equal to delta. That makes them interchangeable. We already know that this value is less than delta. And since we know that this value right here is less than or equal to this value from this inequality, right? Here's that value from the left and here's the value from the right. This one is always less than this one. Then we know that this is also going to be less than delta. And we know that this value is also going to be less than epsilon. What that tells us is that if given a certain radius here, a certain radius for delta, and we have this circle around the point AB, that defines a certain range here for epsilon, a certain distance that we can move away from L. Well, now all we have to do is shrink that circle. If we make that circle smaller, we bring in the value of delta, we make the value of delta smaller, and we make the radius around this point AB smaller, that's going to shrink our interval for epsilon, and maybe we're only going to be able to go from here to here around the point L. So that epsilon range gets narrower as the delta range gets narrower. In other words, if epsilon equals delta, like we said, we picked that arbitrary value, and we start pulling in that value, we start making delta smaller, then epsilon's going to get smaller too. As delta and epsilon get smaller and smaller and smaller, what we're showing here is that we approach L, we approach the limit L, as we approach the point AB, thereby proving that the limit of this function as xy approaches the point 0, 0, the point AB, of this particular function, that it is in fact equal to L, and of course that means equal to 0, the value we found before. So we can say that the limit as xy approaches 0, 0 of our function xy over square root of x squared plus y squared, that the limit is equal to 0.